Standing waves are actually created fairly often in natural situations. Let's take a string, for example. Let's suppose I tie a string between two rigid posts, okay? And for example, this could be a violin string that's tied across the violin, and it's rigidly attached at two places, okay? Then when you bow a violin string, you're just pulling it up at a certain spot, causing a vibration to occur across it. So you're like plucking it, and that pluck will travel back and forth. And so for the standing wave, we saw that in order for a standing wave to occur, we have to have a wave traveling this way and an identical wave traveling the other way, and the timing seemed to be important. But what happens in this natural situation, this easy situation, is when that wave gets to this side, it reflects, it rebounds. And so as a downward pulse tries to pull down up here, the rigid wall says nope, and by Newton's third law, we get a push backwards that actually pulls it back up, and so it ends up being exactly in the right form for us to get that standing wave. Same thing happens in pipes, and like open, air pipes, so like an organ pipe or even a tuba that's all bent up, but it's based on the boundary conditions that cause these standing waves to occur naturally without any difficulty in contriving a mechanism. And so with that understanding that they happen very easily, we can write out our displacement equation for those left-going wave, or the right-going wave and the left-going wave, and see that we don't really care about how we start those waves. They'll automatically create a standing wave. So let's suppose we have the right-going wave and the left-going wave, and their displacement equations would look like this. So d, I'll call it dr, is going to be equal to the amplitude times sine of, I'll use the simple forms, the wave number times x minus omega t, and then plus this phi 0 for the right-going wave, and d left is going to be equal to a sine kx. Since it's a leftward going wave, instead of having a minus sign, we have a plus sign, omega t plus phi 0 left. And those natural boundary conditions that cause reflections of this wave at just the right time mean we don't care about how they start. They will automatically overlap each other at the right timing, and so for whatever time we start, they're already doing that. So we only need to worry about their position and time. Okay, so as they're overlapping through superposition, the total displacement function is just a sum of these two. So our displacement function is dr plus dl. Okay, and writing that out, we can see that it's going to be a times sine of kx minus omega t plus sine of kx plus omega t. Okay, and if you enjoyed your trigonometry, you'll see that that has some trig identity, a trig identity we could play with there. It just so happens that if you think of this as sine of a minus b, and this is a plus b, okay, these two values are the same, these values are just different with the sign in between them. Well, sine of a minus b is the same thing as sine of a times cosine of b minus cosine of a sine of b, and then the same thing's true here, only it's a plus instead of a minus. So this ends up equaling a, okay, converting that, we get a sine of a, which is kx, times a cosine of b, which is omega t, okay, minus, because that minus sign, and then reverse these, cosine of kx, sine of omega t. Okay, and then we do the next one, which I'm going to have to be a little bit tighter to fit it across this page. Okay, then we're going to have plus, that plus right there is plus sine of kx, cosine of omega t, plus I'm going to jump down here, cosine of kx sine of omega t. Close that bracket. Okay? So these two terms came from the trig identity for this term, and these two terms came from the trig identity for this term. Alright, well, looking at that, we have a little algebra to do. We see that we have a minus kx sine of omega t, or cosine kx sine of omega t, and a plus cosine of kx sine of omega t. So these two terms cancel. These two terms that are left are identical, so I just have a factor of 2 times one of them, and ultimately I end up with d is equal to 2a sine of kx times cosine of omega t. Alright? And right away from our previous work we did, we see that there's no more traveling information here. This piece of it is all dependent on position and independent of time. And then this piece of it is independent of position and only dependent on time. And so we often call this whole thing a of x, and we call it the amplitude function because it depends how big the string is going to go. The maximum displacement of the string will go at every position x. And then the cosine of omega t says how it oscillates between that amplitude and the negative amplitude. And so this gave us that shape that we saw before. Now, if this is our string, that it would look like these bumps are just oscillating back and forth, such that at twice in a cycle, the string is absolutely flat. And then these bumps just alternate positions. So it goes from here to here, and it never moves side to side. They just go back and forth. And so this envelope here, okay, that we see is given by this function, and then the timing of how they oscillate back and forth is given by this function. Okay, so this is now our displacement equation for a standing wave and shows mathematically what we saw earlier by doing some simple superposition.